Hey, what's up, and welcome back to the series AI Concepts with Coding from Scratch. In this video, you will learn what is a neural network activation function and how does it work. We're going to explore different types of activation function and learn how to pick the right one as well as the implementation using PyTorch. If you want to learn Python, data science, machine learning, and GenAI, subscribe my YouTube channel. What is a neural network activation function? An activation function decided whether a neuron should be activated or not. This means that it will decide whether the neuron input to the network is important or not. The role of an activation function is to derive the output from a set of input values fit to a node or a layer. So what exactly is a node? Well, if I compare the neural network to our a brain, a node is a replica of a neuron that receives a set of input signal. The primary role of an activation function is to transform the summed weight, you can see summed weight input from the node. You can see input from the node. Input number 1, input number 2, and up to n. An output value to feed to the next hidden layer or as the output. Let's take one real world example. Let's say one mosquito bite in my hand. So what happened? Our skin nerve system send a signal to this brain, and inside the brain is nothing but combination of some kind of neuron. And neuron is nothing but taking the signal, and after that it will giving the response to our another hand to kill the mosquito. So this is how our human brain is actually work. Just like artificial neural network is also working like that, but in a different manner. If I break through down this architecture, the neural network architecture is nothing but a combination of the weight and the biases. And also it will taking some input inside our node. This is called the node, and inside this node we have the weighted as well as input and also adding some biases. And also it will pass into inside an activation functions. Okay, so this is the summit weight, and it is nothing but the input taking from here x1, x2, x3, and based on the each input the weight is initialized. Okay, weight is initialized, and this is called a node. And after that it will give me the output called the a. If you don't understand the concept of neural network and how they work, digging deeper into the topic of activation functions might be challenging. That's why it is a good idea to refresh your knowledge and take a quick look at the structure of the neural network architecture. A neural network architecture is combinations of the input layer, several hidden layer 1, hidden layer 2, hidden layer number 3, and also having one output layer. So what is the input layer? The input layer takes a raw input from the domain. No computation is performed at this layer. See, no computation is performed at this layer. That's mean no weight and the biases is calculated in this input layer. It's just taking the input from the raw domain. Okay, and after that we have the hidden layer. As the name suggests, the node of this layer are not exposed. You can see it. They provide an abstraction to the neural network. And in the hidden layer, all of kind of computations on the feature enter through the input layer and transfer the result to the output layer. This is the work for the hidden layer. And inside this hidden layer, all of the weight and the bias is calculated, as well as it will passing all of the data from output layer as well. This is called the back propagations. So in a neural network, two things is happen: forward propagation and another one is called the backward propagations. And in the output layer, you can get the output or the final output of the layers. Okay, so what is the feedward pass? I mean, feed forward network, and what is the backward or the back propagations? Forward is nothing but calculating the weight and biases, and backward is nothing but getting back and update the weight of the neural network architecture. Why do neural network need an activation functions? Well, the purpose of a activation function is to add the non-linearity to the neural network architecture. Activation functions introduce an additional step at each layer during the forward pass and the backward pass as well. Let's suppose we have a neural network without using the activation functions. So what will happen in the case every neuron will performing a linear transformations on the input using the weighted and biases. It because it doesn't matter how many hidden layers were attached in the neural network. All the layers will behave in the same way because the composition of the two linear function in a linear function itself. There are three types of neural network activation function is widely used. The first one is called the binary step function. Second one is called the linear activation functions. So what is the binary step function? Binary step function depends on a threshold value that decided whether a neuron should be activated or not. If I see the formula of the binary step function, if the input value is less than 0, it will simply making as a 0. If the value is nothing but greater than 0, it will making this as a 1. So what is the linear activation function? The linear activation function, also known as no activation, or the identity functions, because it multiply with just an x. Is higher the activation function is proportional to the input. At binary step function as well as the linear activation function, it having some limitation. In binary step function, it cannot provide the multi-value output. For example, it cannot be used for the multi-class classification problem. See, multi-class classification problem. The second one, the gradient of the step function is 0. You can see gradient of the step function is 0, which causes a hindrance in the back propagation process. In the back propagation process, you cannot using these binary step functions. The second one is called the linear activation functions. So however, a linear activation function has two major problems. Number one problem is it is not possible to use a back propagations, as the derived to the functions is a constant and has no relations to the input x. Okay, you can see that. That's what's called the no activation function as well. All the layer of the neural network will collapse into one of it. A neural activation function is used. Now I'm going to give you one example in the Google Colab. You can see that why we don't need to using here these linear activation functions, and why should you need to using here these non-linear activation functions. That's called the Sigmoid, Tanh, ReLU, Leaky ReLU, Parametric ReLU, SELU, Softmax, Swish, GELU, and SELU. Now, those are the activation functions that you can use in the neural network. And why? Let's discuss it in the Google Colab. In the real world scenario, your data is not in the form of linear. So I'm going to getting here differentiation between the linear activation functions as well as the non-linear activation functions, just like ReLU or the Softmax or Sigmoid. So I'm just taking one examples, and here we're going to creating some linear data set, and I'm just going to using here and linear activation functions that you can see on here. And after that, I'm going to using here this optimizer and the loss. If you need the complete video about the different kind of optimizer and the loss, just comment below so that I can also creating one a video regarding that, because this is an AI concept series, right? So you can see here we have one decision boundary which are creating on best fit line, and it will dividing with all of the values or all of the features in using one best fit line. Okay, you can see best fit line. Okay, boundary. See, because this is a linear data, we can simply easily actually classify it out. Okay, let's say I have a non-linear data set. See, I just using here linear, but you're going to creating here on last non-linear data set. Okay, just having some noise on that. So what you can see, it will, yes, it will creating the layer, or it will create the best fit line. The problem is some of the data is missing. Some of the data is missing on here, and some of the data is go inside this blow lines dot. Okay, blow line feature. That's mean in the case of linear data set, it will working fine. But in the case of non-linear data, it will not working. So this is the advantage of using the activation functions in the neural network. See, without activation functions, you cannot getting this data as well. So now let's say I'm going to using here some non-linear types of data. Okay, so what will happen? You can see I'm creating here some a non-linear data set, just like the same thing, but I'm using here the ReLU as an activation function, which one is nothing but a non-linear activation function, as well as a sigmoid. You can see two activation function. I'm going to use it here. Now, if I see the output, that you can see it will creating some non-linear boundary on here. You can see non-linear boundary. Okay, how cool. Okay, it will try to classify them, the decision boundary for that. But if you see in the non-linear data set, it will just getting here on best fit line and getting on boundary. So this is why I'm not using this linear activation function in the case of neural network. Okay, so that's why you need to using here this ReLU or the ALU or the sigmoid, this kind of non-linear structure of data set. And this is also one importance of using these activation functions in the neural network. So now what I can do is simply going to discussing all of the non-linear activation functions in details with the coding. So our first non-linear neural network activation function is sigmoid activation function, or you can say the logistic activation functions. So let's try to derive it more and try to implement this sigmoid activation function using PyTorch. The sigmoid activation functions takes any real value as the input and output value in the range of 0 to 1. And you can see here the shape of the sigmoid activation function is look like the S. The larger the input, more positive, it is closer to the 1. You can see closer to the 1, whereas the more negative value or the more smaller value it is closing to the 0 that you can see on here. So this is the formula of the sigmoid activation functions. 1 divided by 1 plus e to the power minus x. This is the formula of the sigmoid activation functions, but they are also having some advantage as well as having some limitation as well. Sigmoid activation function is the right choice because of its range, and it's also having some advantage. The number one advantage is it's commonly used for model where we have to predict the probability as an output. See, probability as an output. That's been in the output layer. Since the probability of anything exists only between the range of 0 to 1, that's mean binary classification problem, we can using this sigmoid activation functions. Number two, the function is differentiable and provide an smooth gradient. See, smooth gradient differentiable because the non-linear activation function should be differentiable. Otherwise, it's not a non-linear activation function. You cannot use it. Preventing jump into the output value. Now, why differentiable? Because see, our neural network architecture or the neural network is nothing but using here one technique called the back propagations. In the back propagation, it will try to draw the derivative of that. So that's why non-linear activation function should be the having the derivations of that. So preventing jump in the output value in the gradient descent. This is representing an S shape in the sigmoid activation functions, but it also having some limitations. If I going to derive this activation function, we having getting one formula sigmoid of x into 1 minus sigmoid of x. And if I see the graph of that, the gradient values are only significant in the range of minus 3 to 3. See, minus 3 to 3. And also the shape of the gradient is look like the flat. Okay, the function will having very small number of gradient. So as the gradient values approaches to the 0, because see the range is so little, so flattened, the network cases to learn and suffer from the vanishing gradient problem. So what is the vanishing gradient problem? We'll explore it later on. So those are the problem actually happening in the case of sigmoid activation function. That's why the output of the sigmoid function is not symmetric around the 0. It's not 0 center. That's why 10s is coming into the pictures. So now what I can do is simply going to coding these sigmoid activation functions using PyTorch. Well, so now what I can do is simply going to implement the sigmoid activation function from scratch using PyTorch. So let's importing here the torch. Let's say import torch. Then I'm going to importing here the matplotlib. Let's say import the matplotlib dot pyplot as plt. And then I'm going to using here a style. Let's say plt dot style dot use so that it look like cool. And then after that, I'm going to creating here a class called Sigmoid. Let's create a class and it should be the Sigmoid. And then I am simply going to do the initializations one. Let's call def init. So we're going to passing here. We're going to passing here the self itself. Self. And after that, we're going to creating here the super. Let's say inside the super, it will inherit the Sigmoid activation functions. And then it passing the self. This is a basic building block. Okay. And let's use the init. That's it. Now inside this initialization part, you don't need to initialize anything because it's not taking any variables. So you can simply go into creating the forward pass. So in the PyTorch, when you're creating the class, you need to using it inside the forward pass because PyTorch is just actually working like that in the form of derivations or the back propagations. So that's a def forward. And inside that, we're going to passing here the self and the x itself. Now we're going to implementing here our roles or the formula of the sigmoid activation functions. The formula of the sigmoid activation function is 1 divided by 1 plus e to the power minus x. So let's say I'm going to return it. Let's say return here. We're going to 1 divided by 1 plus torch.exp. Let's say torch.exp. I mean exponential of the minus x. This is how our sigmoid activation functional actually formulas look like. Now what I can do is simply going to running this out, and after that I'm simply going to call in the sigmoid activation functions, just getting here one instance. Let's say sigmoid, let's say layer is nothing but the sigmoid. Let's say sigmoid. Okay, so you're just getting here an instance of the sigmoid, and if I see this sigmoid layer, you can see on that this is how the sigmoid layer actually look like. And if I'm going to passing here some of the value inside this activation functions, let's say I'm going to creating here some random value. Let's try to creating here, let's say x equal to torch dot, let's say linspace, just can take here linspace, and let's say lean space, and inside that you can passing here, let's say minus 10 to 10 at differentiate of the 100, and then you can passing it inside the x, let's say x equal to, and we can, it's nothing but our y. Okay, so this is applying here the sigmoid activation function. So we can do it in the same line, we can do it in the same line, and you can do it in the same line. Okay, so why the x and y? So that you can also painting this out. So let's try to deleting this out and see the activation functions of that. And then you can see here sigmoid object is not callable. You can see it's not callable. uh okay, sigmoid layer, you're passing here the x, so it also passing here one thing that's called nn.module. So let's say nn.module, and it also importing this out, let's say module, and then I am simply going to actually use import it, the torch.nn. Let's import torch.nn as nn. Okay, so why? Because this torch is nothing but using here on backward pass. That's why this NN or the neural network model is important. If you can you do, if you it's not doesn't matter that you don't using the built-in, but use you actually creating this out. Okay, you're creating this out. You inherit this NN dot module on here, this neural network model, because it will actually using the forward pass. Okay, in here. Now you can see here we having the sigmoid activation functions, because the sigmoid activation function is also calculate the derivative that you see on here minus 3 to 3. So that's when to passing here this nn dot module. So we have the y, we can printing this out y to see the value, and this is nothing but the value for the activation functions. So if you're going to passing here just one single value in the torch, you can also getting here the derivative of that. You get the derivative sigmoid of x into 1 minus sigmoid of x, just like that. Okay, so this is the derivative of that. Now what I can do is simply going to plotting this out, so it will be better. You can see the shape of the sigmoid activation functions. So what I can do, if you need the videos regarding PyTorch, you can also comment below, so that I can also getting here one comprehensive course in the case of PyTorch, that how the PyTorch actually look and how the PyTorch is calculating the derivative. Okay, so plt.plot, and then inside that I can passing here x.numpy, because x is nothing but our uh, input column and the target column is y. Let's say numpy, so that you can do the plotting, because while you do the plotting you have to pass it in there from the numpy. And after that we can giving here on level, let's say plt dot x level, and inside it you can passing here the x, and then I'm going to passing here plt dot y level, and y level is nothing but called sigmoid of x. Let's say sigmoid of x, and after that you can adding here title. Let's plt dot title, it's nothing but called sigmoid activation function. So you can div it to here, we can copy this out because we are lazy as well. And then I am simply going to giving here a grid, so that you can see in the form of grid as well. Let's say grid, and making as a true, and then you can make it plt.show. Now you can see, just wait few seconds, it will creating here on plot, and you can see the plot is look like that. You can see the shapes look like the s that you can see in the slide as well. And this is the negative one, and this is the positive one. Positive is up to 1, it is more positive, it will just going for the near to the 1. It's more negative, it will go to the zeros as well. You can see on here. So this is how we can implementing here the sigmoid activation functions using the PyTorch. So why I chose the PyTorch? Because in the PyTorch it having some features called the backpropagation process of the forward pass and the backward pass, and auto grad it's called the gradient. So that's why I just choosing this library for creating this one. Make sure you passing here this n dot module, okay? Because it is inheriting this one, I have to also calculate the derivative of that in the non-linear activation functions. Now let's try to implementing here our next one that's called the tan-h activation functions. So our next activation function is tan-h activation functions, also called the hyperbolic tangent. So tan-h activation function is very similar to the sigmoid activation functions, as it even has the S shape that you can see on here, with the difference output range is nothing but -1 to 1. In the sigmoid activation functions, the range is lies between the 0 to 1, and in here it lies between the -1 to 1. That's in more positive value it will close to the 1, more negative value it is close to the -1. And this is the formula of the tan-h activation functions. So you have the ex minus e to the power minus x divided by ex or e to the power x plus e to the power minus x. This is the formula of the tan-h activation function. There are some advantages of using the tan-h activation functions. The number one is the output of the tan-h activation function is zero center. Zero center means the value is normalized because the value is lies between to the -1 to 1. So this is nothing but on a standard format of the normalization. So that's what's called the zero center. As well as in the sigmoid activation functions, the values is lies between the 0 to 1. That means you cannot easily map the output value as strongly negative in the case of sigmoid. But in the case of tan-h, you can easily map the output values as strongly negative, neutral, and strongly positive as well. So this is the benefit of using the tan-h activation functions. Now the question is how the tan-h activation function is basically used. It's used in the hidden layer of the neural network, as its values lies between the -1 to 1. So therefore, the mean of the hidden layer, therefore the mean of the hidden layer comes out to be 0 or very closer to it. See, the mean of the hidden layer comes out to be 0 or very close to it. That's mean it's normalized, or it's called the zero center. So it's helping in centering the data, centering in the data and make learning for the next layer much easier. So that's why the tan-h activation function is used. See, it's zero centered, but the sigmoid is not zero centered at all. But in the non-linear activation function, it should be the zero centered. Now, what are the limitations of the tan-h activation function? Same thing in the sigmoid activation function. If I derive them, in the case of tan-h, it's also have the range between the -3 to the 3, -3 to the 3, and also the graph is look like not so flatter than the sigmoid, but it's flatter. And if I derive them, we got in this one tan-h up to 2x. So it's also having some problem called the vanishing gradient problem. This is actually happening in the case of tan-h as well. So that's why ReLU is coming into the pictures. So now what I can do, I am simply going to implementing these tan-h activation functions and try to implementing this one using PyTorch. Well, same thing. I'm going to importing those the module because it's needed at all. I don't need to import this one. I can creating here the class called the tan-h because you're importing this charge and torch.nn. So you can simply go into using this one. So what I can do is simply going to creating a class called tan-h. It's a class tan-h and which one inheriting the nn.module. And then after that, I can creating here on def. Let's say def init, and then I'm going to passing here the self, and also I'm going to creating here the super class. So that's a super, and you can passing here the tan-h and the self and underscore init. That's it. Now we don't need to do the initialization on here. We can creating the forward pass. So you can create the forward pass. Let's say def forward, and you can passing here self and x. And after that, we having two terms. One is called the positive term, another one is called the negative term in the case of tan-h activation function. So let's getting here exp of x is called positive one. So you can using here torch.exp of x, and we having one negative case of the exp. So it's called exp negative x. It's called torch dot exp of negative of x. And now we can return in this one. Let's say return here the exp positive minus exp negative, okay, exp negative x, and then we can divide them. We can divide them with the exp positive plus exp negative. Okay, that's a negative of x. This is nothing but the formula of the 10h activation functions. Now you can run in this out, and after that you can simply going to copy in this code. You can copy this code and you can pass it to here, because you can using here the same same range in here for creating here these activation functions. So what I can do is simply going to creating this one called the 10h layer. Let's say 10h layer, and instead of using this one you can pass into here, and this is also be here our 10h. Okay, so now we have it's loaded, and you can see the value of the 10h, and you can also copy the code for this one as well, because all of the code is similar. You can see here this is the value for the 10h activation functions. You can see values is lies between the -1, the lowest value of that. And if I see the one, the lowest value is nothing but going as the 0th. So you can paste it here the code. Let's try to make it as, so you can also see this out. And if I go into plotting this one, you can see here it's called sigmoid. Okay, to changing this one, let's say x comma 1, so that you can see the difference between one. Let's say x comma 1, and let's say y comma 1 as well. Okay, and you should running this one, we need to making as the x underscore 1, or let's say y underscore 1. And if I make it as a 10h, and let's say 10h activation functions, here you go, and you can see the same graph you can see on here. Okay, it lies between the 1 to the -1. You can see on here it's how it look like. Just look like the sigmoid activation function, but having some difference on that. You can see difference on that. Okay, it's quite sloppy, and it's quite look like s, but not sloppy as well. So this is the difference between the 10h activation functions and the sigmoid activation functions. So both are the functions having the vanishing gradient problems. So for that, the ReLU activation function is coming into the picture. So now what I can do is simply going to implementing the ReLU activation functions. But before that, it also learn about the theoretical knowledge of the ReLU activation functions. Our next activation function is ReLU. ReLU stands for rectified linear unit. Using ReLU, it will give some impression of a linear function. So ReLU has a derivative function and allows for back propagations. That's when we can simply using it in the neural network architecture. The main catch here that the ReLU function doesn't active all the neuron at the same time. See, doesn't active all the neuron in the same time. However, the sigmoid and the 10h is activate all of the neuron in the same time. And also one more thing, the neuron will only be deactivated. See, the neuron will only be deactivated if the output of their linear transformation is less than 0. See, if it is less than 0, it will making it deactivated. You can see less than 0, it is making it deactivated. And if it is greater than 0, it will taking the as it is value or activated. So this is the formula of the ReLU. It will taking the maximum of the 0th comma x. So 0 is nothing but for the negative. That's mean if the value is negative, it will directly making as a 0. And also if it is a positive value, it is just taking as it is. Okay, this is the formula of the ReLU. But in ReLU, it also having some limitations as well as it having some advantage. The first one limitation is called it will having some problem called the dying problem, because all of the some of the value, some of the neurons should be deactivated. It can be it possible also that 50% of the neurons should be deactivated as well. So this is one problem in the ReLU. So it also having advantage. Let's discuss about the advantage first. The first advantage is since only a certain number of neurons are activated, the ReLU function is far more computationally efficient when compared to the sigmoid and the 10h function. Yes, it's true that in computational purpose we can using the ReLU, because we don't need to using here the multiple number of or the complex types of competitions, because in the sigmoid and the 10h all of the activation function is activated. But in here ReLU, certain number of neuron are activated. If the value is passing through the neuron and if the value is greater than 0. ReLU accelerates the convergence of gradient descent toward the global minima of loss functions due to its linear. Because see, I know that those are these non-linear functions, but in ReLU, it's nothing but working as a linear transformation as well. Non-saturating property, the most important thing. So in the ReLU, it having the D advantage. I also talk about that. It's called the de-dying ReLU problem. De-dying ReLU problem. So why it happening actually? See, because of that, if I'm going to a derivative this one, and we see that if the value is less than 0, all of the neuron is deactivated. Let's say I have the 100 neuron. It also be possible in the worst case, 100 neuron is deactivated, and also deactivated, so it will give me some kind of problem. It maybe happen that for the 100 cases also, when the neuron is deactivated, it's not activated yet. Okay, that's when how once it is deactivated, it's not activated in the whole program. So that's one problem in the ReLU. So I giving here one note to removing this problem in just for a certain way. For building the most reliable machine learning model, split your data into train, validation, and the test set. Yeah, we already do this kind of thing while building the machine learning model or the neural net architecture. But in here, ReLU, you need to follow this one. You know, to removing this dying ReLU problem. See, I'm going to revise it more again in Hindi as well. देखो डाइंग रेलू प्रॉब्लम क्या क्यों होता है? देखो ऐसा हो सकता है क्योंकि रेलू काम करता है, कुछ न्यूरॉन डीएक्टिवेट हो जाता है रेलू पे, तो इसलिए जो कंपटीशन है ना वो बहुत इफिशिएंट होता है, बहुत स्पीड होता है। लेकिन प्रॉब्लम है देखो, वर्स्ट केस में 100 न्यूरॉन भी डीएक्टिव हो सकता है। देखो नहीं होगा इसका मतलब क्या है, हो सकता है। हाँ, तो इसका बाद क्या होगा, न्यूरॉन भी नहीं है, एक्टिवेशन फंक्शन भी नहीं है, तो एक्टिवेशन फंक्शन नहीं होगा तो लीनियर की तरह काम करेगा, लीनियर रिग्रेशन की तरह काम करेगा, तो वो बहुत प्रॉब्लम है। और एक प्रॉब्लम है क्या, देखो 50% मेरा न्यूरॉन डीएक्टिवेट हो चुका है, तो इस तरह में जो डीएक्टिवेट हो चुका है वो एक्टिव और नहीं होगा। ये बहुत 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 प्रॉब्लम है रेलो का। ओके, तो इसलिए इससे बचने के लिए तुमको क्या करना पड़ेगा, आपका डेटा को ट्रेन, वैलिडेशन और टेस्ट में डिवाइड करना पड़ेगा। नाउ वी सिंपली गोइंग टू बिल्डिंग दिस क्लास कॉल्ड रेलो। Okay, so let's create a class called ReLU. Let's say ReLU which one taking nn.module, and then after that we can using here def, let's say init, and then I'm going to passing here the self, and after that I'm going to passing here the super keyword and inside the ReLU, and then we have the self and dot underscore init. If I get more support in this series got called the AI concepts with coding from scratch, probably more things will be coming just like from a scratch. It can be the LSTM from the scratch, it can be the RNN from the scratch, it can be the stable diffusion, or it can be the llama model. So let's say def forward, in the forward pass, just I need support. That's a self and comma x. Okay, that's it. Then after that, what I can do is simply going to be returning here the torch dot maximum, because it's taking the maximum of the value is coming and with the 0, so it should be maximum. The value is coming, let's say torch dot tensor, because this is a PyTorch, you need to convert them into tensor, otherwise you cannot visualize it. 0.0, then the value is coming here as the parameter, that's x. Now you can simply go into creating here layer, let's say ReLU underscore layer, and we have the ReLU. Okay, ReLU, and then what you can do, you can simply go into copy this out. The same thing we exactly do it here. We can copy it from here, so we can paste it to here. Instead of the 10h functions, you need to make it as a, we can make it as simple as that same variable name in a space, and we passing here the ReLU activation layer. Okay, on here, and then I'm going to passing here the code for the graph. So this is one, and you can copy, and here you go, you can passing this. Okay, it's better you can running this out first, because while printing here the y, then you can see one more important thing, you can clear about the data. Okay, let's try to, you can see here the maximum value is nothing but is up to 10, and the minimum value is nothing but the 0, because we give it here 10 as the nothing but output of the maximum value. You can see on here, and minimum is 0. It's not going the less than 0. Okay, so we can now printing this out, and you can passing here x, and this is the y, and instead of the 10h you can pass it here ReLU, and it should be the ReLU activation functions, and you can see like that now. And you can see the graph is exactly the same that you see in the presentation slide. You can see after 10, I say after 0, it will give me the dying problem. Okay, it's not activated yet. And the most actually maximal is I think 10, because we pass it here 10 as well. So you can see on here. Okay. So this is how the ReLU is actually used. ReLU is basically used in CNN architecture mode because it's really convenient to using this ReLU. Okay, and in CNN or the hidden layer or the neural architecture, we actually basically using the dropout layer as well to deactivate some of the neuron. So for this case, you can also using the ReLU as well. Now I'm going to discussing about here the next one, that's called the Leaky ReLU. So our next activation function is Leaky ReLU. Leaky ReLU is an improved version of ReLU function to solve the dying ReLU problem, as it has a small positive slope. You can see a small positive slope. You can see on here in the negative area, because the dying problem is happening in the negative area. Now see why the dying problem actually happening, because of most of the activation function is deactivated. Why? Why deactivated? Because weight is not updated. In the back propagation, our weight should be updated. In the back propagation law, we see that we have on learning rate, we also having on derivative, right? If the derivative is zero, I mean this part is zero, derivative is zero, we cannot update the weight. So that's why all of the neuron is deactivated. But here we can see here we adding here one extra value called 0.1. That's mean our weight is not going to go inside the 0. It will just making at a value, simple value called the 0.1. That's mean what should be updated. What should be updated. So this is a formula of the Leaky ReLU, max of 0.1x and x. Leaky ReLU and the ReLU is mostly similar, just having one parametric difference of the 0.1. So it having also advantage as well as also having the disadvantage. So let's see. The advantage of the Leaky ReLU are same as the ReLU, because we see that in the ReLU we can use it in the back propagations. So in the additional to fact that it doesn't enable back propagation even for negative input value. You can see here. Okay. And by making the minor modification of the negative input value, the gradient of the left side of the graph comes out to be non-zero value. We also already talk about that. Therefore, we would no longer encounter that neuron in the region. Okay, in this region. So this is the derivative of the Leaky ReLU. You can see on here. Okay, slope is simple slope. That's been in the ReLU we having some problem based on the negative values, because it will go into the dying problem, and in here the problem is solved, but it also having some limitation. The prediction, see, the prediction may not be consistent for the negative input value. Yes, it's one greatest disadvantage, because while I do the predictions, the negative value is not consistent. The second one, the gradient for the negative values is a small value. You can see 0.1. Okay, 0.01, a small value that makes the learning of the model parameter time consuming, because the weight is so small. Yeah, we can update the weight, but it's really time consuming. This one limitation of the Leaky ReLU. So let's try to do the coding of the Leaky ReLU first. It's similarly as the ReLU, just having one minor changes on here. Now let's go on the Google Colab. Okay, let's create a class called Leaky ReLU. Let's a class Leaky ReLU, and you can passing here nn.module, and then let's getting here dev, let's say init, and then we're going to passing here self, and we're having a special parameter called alpha. Okay, alpha is equal to 0.01 or 0.1. Let's say 0.1 that you see in the example, and after that you can pass in here the super, and then you can pass it here the Leaky ReLU. Let's say Leaky ReLU, and then you can pass in here the self and dot init. So this is nothing but the value, I mean 0.1. It's for the slope. Okay, it will just giving here a slope in the negative value. Just I'm going to passing it a variable called alpha. You can also pass it to here. It's learnable parameter as well, but it's not like that. But in the Leaky ReLU, value is constant. Also, you can make it a learnable. So I'm going to passing here self dot alpha, alpha equal to, let's say, alpha, and then after that I'm going to return it, let's say, def forward, forward, and after that I can pass it here self comma x. So I'm going to return here, let's say, return here torch dot higher. I'm going to using here torch dot higher. So torch dot higher, if the value is greater equal to 0, I am simply going to making it as a x. Okay, otherwise I'm going to making it as a alpha into f. Okay, let's self dot alpha into x, because it don't have any 0. If it's a greater than 0, it just simply going to making it x. Otherwise I'm going to making it as a alpha into x. Alpha is nothing but 0.1 that's mentioned on here. Now I am simply going to creating here a layer for Leaky ReLU. Let's say Leaky ReLU, and it should be the Leaky ReLU. Let's say Leaky ReLU, and after that I am simply going to using here the same code that we using it here. So we can copy this out, and you can also checking this out the value of the Leaky ReLU. So it should be the Leaky ReLU, and I'm going to remove this out. Okay, so we can simply go into printing it out later on. So here you go, and you have the y. Oh, y should be the small. Y I pass it to the capital. Yeah, caps lock is on, that's why. And you can see that the value is nothing but -1. For the minus, it's nothing but also calculated. You can see on here. Okay. Now you can simply go into printing this out. I mean, visualize this out. So I'm going to copy this out. Same thing, and I'm going to paste it to here. And it should be the Leaky ReLU. Let's say Leaky ReLU. Then you can see the same graph that you see in the presentation slide as well. Little bit slope on here. Little bit slope. Okay. So this is all about the Leaky ReLU, that how it actually work. Now I am simply going to creating here uh, another important activation function that's called the parametric ReLU activation functions. So we have one value called the alpha, and which one is not learnable. But in this case, after in the parametric ReLU, we have a parameter called the alpha as well, but it's learnable. So our next activation function is parametric ReLU function. Parametric ReLU function is another variant of ReLU that aim to solve the problem of gradient becoming 0 for the left half of the axis. In the ReLU activation function, the left half of the axis is becoming 0 and causes one problem called the dying problem or the dead neuron. The function provides the slope for the negative part of the function as the argument. Okay, by performing backpropagation, the most appropriate value of A is learnable. See, here A is a slope parameter for the negative value. That means for the backpropagation purpose, this A is learnable. Here the Leaky ReLU A or the alpha is not learnable. But in here parametric, we need to using here one learnable parameter for the ReLU activation function called the parametric ReLU. In the parametric ReLU function, it having the advantage as well as it having some limitation. The parametric ReLU function is used when the Leaky ReLU function still fails at solving the problem of dead neuron, because it is time consuming. I mean the Leaky ReLU, because it having a small number of weight, and the relevant information is not successfully passed to the next layer. Okay, because it's time causing, and sometime it will not give you the constant value, I mean consistent value. The function limitation is that it may perform differently for different problem depending upon the value of slope parameter called A or the alpha. Okay, for different problem you have to pass in here different times of parametric value. This is one limitation for that. Now I am simply going to creating here these parametric ReLU functions using PyTorch. So let's create a class called parametric. Let's say class parametric ReLU. Let's say let's make it as a ReLU like that. And after that, you can pass in here nn dot module, and then we can create in here def. That's init, and then you can pass in here the self and the alpha. So let's say by default I'm going to pass in here alpha as 0.1. You can pass it here any kind of alpha value. Then I'm going to make it as a super, and I'm going to pass in here the parametric ReLU. Okay, let's see parametric ReLU, and it should be self, and then you can using here underscore underscore init. Okay, and then I'm going to creating initialize here our alpha value as a learnable parameter. So I'm going to using here self dot alpha. By default, we're passing here the value for the alpha, but in here for the initialization, you need to also making it as a learnable parameter. So I'm going to using here nn dot parameter. If you wanted to making any parameter learnables, so you can using here this nn dot parameter module, and inside it you can passing here torch dot tensor of alpha. Okay, let's say tensor of alpha, and then you can making as a d type, or the data type is called torch dot float 32. That's a torch dot float 32. Okay, here you go. Now you can simply go into creating here a forward pass. Let's say def forward forward, and you can pass in here the self and the x, and after that you can simply go to returning here torch dot here, same thing, torch dot here. If the value is nothing but greater than equal to 0, then you can making it x, otherwise you can making it alpha into x. That's alpha into x, same thing. So you can now copy this code from here, because all of the things are same. Just we have one learnable parameter, pass it to the nn dot parameter, and it should be the parametric ReLU, and it should be the Leaky ReLU should be passing at a parametric ReLU, and we having this one, we can passing it out, and you can painting this y, and after that you can copy this same thing from here. So you can see here all the values nothing but for the, you can see higher backward 0. Okay, gradient function, because this is learnable, but in here you don't get anyone, you can don't see anyone. Okay, don't see anyone, because this is this value of the x is nothing but called is calculate the derivative as well as it is learnable. That's why. So I'm going to making it as a this one, and this should be the parametric ReLU, parametric ReLU. That's it. Okay, it should be parametric ReLU as well. Copy this out, and I'm going to making it as a here, and if I doing any mistake in here, yeah, it should be the Leaky ReLU as well. So I'm going to copy this out, I'm going to make it here, and let's say Leaky ReLU, and this is one parametric ReLU, and try to plotting this out, and we can see the slope of that. Okay, cannot call the numpy of tensor, just required to get use tensor detach dot numpy instant, because say this is learnable parameter, so that's why we're using here one thing that's called detach. Okay, so I can using here detach, so we're using here this detach, so that's a detach. Okay, detach dot this one. Now you can printing this out, and you can see here how the parametric ReLU function actually see like that. You can see on here that how it look like. Because why detach? Because this is learnable parameter, also it having some gradient as well, so that's why to using a detach in PyTorch. So this is how you can actually implementing here the parametric ReLU functions. Okay, so you can pass it in any kind of value. So if I run in this again, and again, and you can see here the same curve. You can also give it here, pass it here your custom function or custom alpha value on here. You can pass it here. Okay, now what I can do is simply going to creating here our next activation functions called SELU. So our next activation function is SELU, also stand for exponential linear unit. So exponential linear unit, or SELU for short, is also a variant of ReLU that modify the slope of negative part of the function. देखो प्रॉब्लम क्या हो रहा है, यहाँ पर नेगेटिव स्लोप है ना, उसके लिए प्रॉब्लम हो रहा है बस, इसलिए इतना सारा यहाँ पर एक्टिवेशन फंक्शन चलाया. So LU uses a log curve. See, LU uses a log curve to define the negative value, unlike the Leaky ReLU and the parametric ReLU. It's just having a log function with a straight line. See, with a straight line. Okay, with a straight line. If I see the curve of the parametric, it's nothing but not a straight line. It is parameterized. And if I see the Leaky ReLU, it's also one straight line. You can see here. Okay, straight line, but not this kind of way. But in here, you can see here, this is quite a straight line in the negative portion. Okay, so this is the difference between the ReLU, the Leaky ReLU, and the parametric ReLU. So this is the formula of the ELU. You can see here, if the value is greater than 0, it will making as a x. I mean, the same value is passing through here. And if the value is less than x or the less than 0, we're simply going to calculate it using exponential of x minus 1, and also having one parameter called the alpha, just like same of the parametric ReLU activation function. So in the ELU, it having some advantage as well as having some limitation. So the button first, it's called the ELU became the most slowly until its output equal to alpha. So higher as ReLU sharply smoothest, because ReLU in the ReLU it having some of the neuron is deactivated. So that's so it's sharply smoothed, and which one is smoothly slowly, which one is one plus point. Avoid the that ReLU problem. It will actually the main problem of the ReLU. So that's why this kind of variant of the ReLU is coming to the picture by introducing a log curve for the negative value of the input. Okay, it's help the network nodes. Okay, see network nodes of the weight and the biases in the right directions. This one greatest advantage of the ELU. Okay, exponential linear unit. The limitation is it increases the computational time because of the exponential operation included. We know that in the DSA, high and hour function is nothing but coming to the exponential, our time complexity and space complexity is introduced. I mean, increases. That's one problem in the types of our in the case of computations. No learning of the A values takes place. Okay, see, no learning parameter level. Exploding gradient problem, which one is a big problem in the case of gradient. Okay, in the last of the video we're going to be discussing about that, what is the vanishing gradient problem, which and what is the exploding gradient problem. Now simply going to creating here this exponential linear unit in PyTorch. So let's create the class called ELU. So it should be the ELU, and you can pass in here nn.module, and then I'm going to using here def, let's say init, and then I'm going to passing here the self, and then I'm going to using here alpha. That's alpha equal to 0.1 or let's say 1.0. In this case, I'm going to just giving here one bigger alpha value, and then after that I can passing here the super, and you can passing here the elu and the self, and let's say underscore init. So in order to set up, I mean initialize the alpha value as alpha, because this alpha is not learnable. This one the advantage of the elu. Okay, because in parameterize the value is learnable. And after that I can creating here the forward pass. Let's creating here forward pass. So forward, so I just give it here 1 just because of so that you can see the graph properly. You can give it here 0.1 as well. Okay, just for simplicity or just showing the graph, I just pass it here 1. Okay, and after that what I can do is simply going to return here passing here the self and the x as well. Let's say self and the x, and you can passing here same thing. Let's say torch.higher, if x value is greater or equal to 0, if the x value is greater equal to 0, we can making it as x, and otherwise we can making it as a self dot alpha into torch. Okay, torch dot exp of x minus 1, that is c in the role. Okay, now I'm simply going to running this out, and after that I can using the same thing on here, and I'm going to making it as a elu, and it should be the elu. Okay, let's say elu relu or let's say elu, and then I'm simply going to making it as a elu as well. but the value should be changes. I'm going to making it as a let's say -5 to 5, -5 to 5, so that you can see the graph properly. And it should be the 2, and now you can pass in here the value, the alpha. You can pass it to here. Let's alpha. Let's say I'm going to give it here. Let's say 0.1. Okay, let's checking this out, and we can running this out, and you can see the y. And this is how it's look like because of exponential. You see, all the value is going to the exponential, and it don't give him here the back guard because it's not a learner parameter. So you can simply going to plotting this out. You can plotting this out, and without using the detach. We don't need to using the detach because it's not learnable parameter. So you can simply going to removing this out. So that's our value. You can see here this graph is not locally like that. Yeah, it's look like the presentation slide, but we can also change this out. We can give it here, let's say 1.0, and see the output clearly that you can see on that. Just wait, you can see here the value is going to up if the I actually increase the size of the value is going to like that, because the alpha value is decreases, and you can see here is the zeroth, and it is going down. You can see on here, but if I'm making it as a 1, it's just like a slightly difference on the axis of the zeroth. Okay, so when actually increase the size, you can see it clearly. So this is how our LU function actually work. LU activation function actually work. So just adding here one log curve. Okay, I'm going to removing this out, and I'm going to running this out. You can also play with them different kind of alpha value. There's one the advantage as well. Okay, you can see on here. You can see here in here also to working fine. But if I'm going to making this one as a just 0.01 or 0.1, it will the slope of the graph of the axis is nothing but so low. You can see so low. Okay, so it's better just using here one uh, capital one, not capital, actually big one. It will give you the perfect output. You can see on here. Okay, now let's go on our next activation functions. Let's go on here. So our next activation function is SELU, also called the scaled exponential linear unit. So SELU was defined in the self-normalizing network and take care of the internal normalizations. That's mean it will working in the case of normalization where you have the mean and the variance. So which mean each layer preserve the mean and the variance from the previous layer. If you see the example, not example actually, if you see the equation of the SELU, you can see here it having two different parameter. One is called the alpha and another parameter called the lambda. Okay, so SELU has both positive and the negative value to shift the mean, which was impossible for ReLU because in ReLU we don't have any output for the negative values. So that's why one problem is occurred. It's called the dead neuron problem. I mean, most of the neuron is deactivated, but in the SELU cases it not happen. So if we see the equation again, if it is a greater than equal to 0, we're simply going to returning this the same exact value, and if it is a less than 0, we're simply going to making it as alpha into e to x minus 1, also having a parameter called lambda. So this is quite interesting activation functions, and it is used in the CNN and RNA as well because so many papers already published based on this scale exponential linear unit. So SELU has a value of alpha and the lambda. They already see that it's predefined. So here are the main advantages of SELU over ReLU. So internal normalizations, we already know that it's faster than the external normalizations. Yes, we also know that the internal normalization is really faster than the external normalization, so that our computation speed is very higher and it not allocated memory as well. So which means the network convergence is faster, obviously. SELU is a relatively newer activation function and need more papers on architecture such as CNN and RNN, convolutional neural network and the recurrent neural network, where it is comparatively explored. Cool. So you can use it, the SELU activation functions, over the CNN and over the RNN as well. Now I'm simply going to implementing these activation functions using PyTorch. Okay, so let's create a class. Let's call SELU, and you're going to passing here nn.module, and then I'm simply going to use here def init and underscore. I'm going to passing here the self and the alpha. Let's pass it here alpha equal to 1.6733. Pre-computed it, predefined, and you have the lambda. Lambda is nothing but, let's say, lambda underscore, because lambda is nothing but a keyword in Python. So let's say lambda underscore, let's say 1.0507. Okay, like that. Okay, 0507. Okay, that's it. Now I'm simply going to actually it should be equal, and then I'm simply going to using here the super keyword. Let's say super, and inside that passing here the SELU, and then I'm going to passing here the self dot underscore init, and then I'm going to adding here self dot alpha is equal to alpha. I just initialize the alpha and the lambda. Let's say lambda lambda underscore. Then I'm simply going to pass it as a lambda underscore. Okay, fine. Now I need to creating here the forward method. So let's say def forward forward, and inside there what I can do is simply going to passing here the self and the x itself, and after that I'm going to returning here torch dot here. So torch dot here, because we have the two clause, if it is greater than 0 or the less than 0. So if it is the greater equal to 0, we simply going to using here self dot lambda, because the lambda should be multiplied with all of the values. So lambda multiply with the x, and otherwise it's simply going to multiply with the alpha and also the exponential and -1. So you can using here self dot lambda, okay, lambda underscore into self dot alpha, and then you can using here the exponential. Let's say torch dot exp of x -1. Let's say x -1. So this is how you can building here the rows of the SELU. Okay, now we can creating here one layer for that. So we can using here instance of SELU. Let's say SELU, and you can passing here the alpha, and you already passing here alpha and the lambda in by default. You can also give it to any kind of lambda or alpha based on your architecture. If you retain paper, you can also implement like this way. So this is called the SELU layer. Let's SELU underscore layer, and then I am simply going to using here torch dot linspace to creating here one input data. Let's say x equal to torch dot linspace. Okay, linspace, and you can pass it here -525, and you give it here the 200, same as that. And then after that I'm going to passing here inside the SELU layer. Let's say SELU underscore layer, passing here the x. So it will give me one value, so which is slice between to the positive and the negative as well. You can see here -1.7460 like that. Okay, so now you can simply going to visualize this one. So you can copy this code because you don't have any learnable parameter, right? So you need to using here the detach. So you can pass it to here, and instead of the ReLU, we can pass it here SELU. It should be SELU. Okay, that's it. Now let's running this out and see the graph. You can see here this graph is exactly look like the presentation slide that you see before, and you can see the minimum is nothing but go for the -2 as well, and -4 in these directions, and positive is going to the 5. Okay, because we give it a 5, and the positive value is nothing but 5.2535, but we give it to the 5, but because of the alpha and the lambda function, it will try to giving here some extra kind of weight and biases. So it is very helpful if you have the 0 rather than 0 weight and the biases. It should be better, we can calculate for the some maximum value. But in the ELU, it has a cheaper number of alpha value. Okay, just have an alpha. So that's also one having a problem, having some advantage, disadvantage as well. Now I am simply going to discuss about the another activation function. Our next activation function is Softmax activation function. But you can see here the graph is look like the Sigmoid activation function graph. Yes, this is the graph of the Sigmoid activation function graph. The Softmax function is described as combination of multiple sigmoid. Multiple sigmoid is combined, and after that we got the activation function called Softmax. So you can use the sigmoid activation function to use in the last layer for the binary classifications, but you use here the Softmax for the multi-class classification. Why I don't use here the sigmoid? That's been one role. One thumbs up rule is nothing but if you have the multi-class classification, you can use the Softmax. If you have the binary classification, you can use the Sigmoid. It's calculate the relative probabilities similar to the Sigmoid or the logistic activation function. The Softmax function return the probability of the each classes. Cool. So it is mostly commonly used in activation function for the last layer for the neural network in the case of multi-class classification. You can see on that. Yeah, if you have the multi-class classification, you can use it for that because it will give you the probability value for the each classes. So this is equation for the softmax, quite simple. We having exponential of z is nothing but this one, and you have the summation of exponential zj. Okay. So now I'm simply going to coding this out, this softmax activation function. It's super simple. It's just like the softmax, just multiple number of sigmoid. Okay, so let's create a class called softmax, and inside there you can passing here nn.module, and you can simply going to make it as a capital. So it should be the s should be the capital, and after that what I can do is simply going to using here the same thing. That's called def underscore init underscore self, and it don't have any parameter, so you can make it empty, and you can pass it inside the super class. That's a softmax and the self, and dot underscore init. Then after that, what I can do is simply going to creating here our forward method because we don't have any parameter. Let's say def forward. We can passing here the self and the x itself, and then we're simply going to creating here calculate the exp of x or exp of z, whatever. So you can using a torch dot exp of x because we're passing here the x, and now we can returning here exp of x and divided by the summation of exp, right? So divided by torch dot sum of exp of x, and inside it we have the dimension. It's a dimension of 0. Now we can simply go into creating here the activation function layer and initialize it. Let's say softmax, and then we can simply go into using here softmax layer, and then we can pass it to one function. So it should be one torch dot linspace. I'm just going to generate some input. Let's say linspace, and let's say -525, and let's give it here 100, and then I'm going to pass it in a y equal to softmax layer, pass it to the x. And after that, what I can do is simply go into printing here the y, and you can see that in the softmax activation function is because of the exponential, the values is look like the exponential as well, log curve. So if I going to printing this out, this one, this is super simple. You can use it for the multi-class classification tasks. So we have the softmax. So it should be the softmax. And if I running this out, you can see the graph how it look like that. Okay, the graph is mostly look like the sigmoid activation function. Okay, but just having some log curve. So that's it about the activation functions, softmax activation functions. Now let's move into our next one. So our next activation function is Swish activation function, and this activation function is built by Google researcher. It is a self-guided activation function deployed by researcher at Google. So Swish consistently match or outperform the ReLU activation function on a deep network, apply it various challenging domains such as image classification and the machine translation. See, image classification is nothing but one kind of CNN task, and machine translation is working based on NLP or the RNN or the transformer architecture. That's mean it will working in two things. One is a CNN, another one is RNN. So if I see the rules of the Sigmoid, you can see here one important thing in the architecture. I mean the graph. You can see it using the Sigmoid. It's using the Sigmoid. You can see that because the sign is look like the Sigmoid is S curve, but if you see that it also having some exponential curve as well. That means if I see that the rules of the Swish is nothing but x into sigmoid of x. Internally, it's actually using the sigmoid. So now let's see the advantage of the Swish activation function. Here are a few advantages of Swish activation function over ReLU. Swish is a smooth function. See, smooth. That means it doesn't abruptly change the direction like ReLU. Yes, ReLU change the direction directly, not smoothly, right? Near to x equal to 0 because it is try to passing here for the negative value as well and try to calculating for the positive value as well. So in the negative value to directly go that, but in Swish it will go to smoothly so that it can calculate the weight and the biases. So it is smoothly beyond to the 0 toward value of 0 and then upward again. Cool. So small negative values are zeroed out in a ReLU activation function. That's with the DAC neuron problem. However, those negative values may still relevant for capturing a pattern underlying the data. That is problem in the ReLU. Large negative values are zeroed out of reason for sparsity, make it a win-to-win situation. Now in this case, see, it will go smoothly जाता है ना, इसलिए weight on bias बहुत अच्छी तरीके से अपडेट हो सकता है. The switch function being non-monotonous, see, and hence expression of input and weight to be learned. That's why Swish is really very one good activation functions. Now we're going to implementing this Swish activation function in PyTorch. So I'm going to creating here a class called Swish. Let's say class Swish. Okay. So let's say nn.module. And then I'm going to using here def of underscore init. And then I'm going to passing here the self. And then I'm going to using here superclass, and inside that I can passing here the Swish and self, and then I'm going to using here underscore init. That's it. Okay. So I don't have any initialization, so you can directly go to the forward pass. Let's say def forward, forward, okay, forward, and you can passing here the self and the x itself. So it is nothing but the taking the sigmoid into x. So you need to creating here the sigmoid activation function first. So you can calculate it like x sigmoid equal to 1 divided by 1 plus exponential of minus. Okay, so torch.exp exp of minus x. So this is nothing but the formula for the sigmoid activation function. Now you can simply go into returning here x into sigmoid. Let's x into sigmoid. That's it. Now you can simply go into calling this out. Let's say Swish, and we can simply go into make it, let's say Swish, Swish layer, oh layer, and then you can pass it to inside one linear space. So let's say x equal to torch dot linear space, and you can pass it to here -525 or let's say 200, so that our graph is look like better. So you can pass it to our Swish layer. Let's say Swish layer, and you can pass it to x, and you can see the y as well. Okay, Swish layer is not defined. It should be a Swish layer layers. So that's why the problem. And after that, what I can do, you can simply go into plotting this out. But you can see that the value is nothing but going to the negative as well. Smooth, you can see a smooth changes. You can see 0.348, then 0.35, 0.362. It don't have any so many gaps. Smoothly it will try to dealing this out. And you can copy this out. And instead of Softmax, you can replace with the Swish. So either page out, let's say Swish and Swish. That's it. Now let's see this one, and you can see that the graph have look like, okay, it have the exponential just like sigmoid activation function. Okay, so this is all about the Swish activation function. Now let's discuss about the last activation function called the GELU. So our next activation function, and it's also the last activation function, is called the GELU. So GELU stands for Gaussian Error Linear Unit. In the graph you can see here we have three graphs. First one is called ELU, second one ReLU, third one is GELU. You see that this is nothing but called exponential unit. So that's why the graph is look like that. And you have the ReLU, it's nothing but a straight line but not visible because of that neuron problem, because after 0 it's not visible. I mean, it's straight line. Then you have the GELU. Also you can see here the exponential height of that here. This is called the GELU. The Gaussian error linear unit activation function is compatible with BERT, another kind of transformer used in the language translations. We have the Roberta, we have the Albert, another top natural language processing model. That's why this GELU activation function is basically used in the tasks of NLP. The activation function is motivated by combining the properties from dropout, zone out, and the ReLU. If you don't know the dropout and the zone out, you can go on the Google and search for that. Dropout is nothing but called deactivating some of the neuron while in the training part. You can deactivate some of the neuron. So this is the equation for the GELU. It's quite complex. You can see here it having the Bernoulli equation as well. It's nothing but used in the problem of binary classification as well. And we merge the functionality by multiplying the input by either 0 or 1, which is stochastically determined and that depend upon the input. And we multiply the neuron input of x by Bernoulli equation, where this Bernoulli is nothing but called p of x greater than or equal to x, and x is nothing but 0 to 1. That's we need to the cumulative distribution functions of the standard normal distribution. You can just go on the Google and search for that. About that, we have the 10h, and we have this one. The equation is nothing but called the Bernoulli equation, and we have the 0.5, and we having one certain value on here. Okay, so now I am simply going to implementing this GELU activation function. So let's create a class called GELU, and inside the vehicle passing here the nn.module, and then I am simply going to using a def underscore init, and then I'm going to passing here the self, and then we have the superclass. You can passing here the GELU, and you can passing here the self dot underscore init, and then I'm going to simply going to go on here forward pass because I don't have any learner parameter or the external parameter as well. Let's say forward, and you can passing here self and the x as well. Now you can simply going to return it. Let's say return here, return 0.5 into x into you have the 1 slash torch dot 10h, because you have the 10h activation 10h as well from the torch, and then you have the square root. If I see the equation again, so you have the 0.5x and 1 plus 10h, and you have the square root 2 by pi and x plus this value 0.04475 and x cube. So let's try to implement this right now again. So let's go on here 10h activation function, then you have the math dot squared, let's say sqrt, and then you have the 2 divided by math dot pi. So math dot pi, math is not important to import it as well. So let's import here the math. Then what do you have? Pi, and then to multiply with this pi, multiply with x plus 0.04475 into x into 3. You can also use the power, math that power. But here you go. You can 0.5 into x, 1 plus torch of 10h. Then you have the math dot squared of 2 divided by pi. And then we have the multiply with x plus 0.044715 into x to the power cube. If I see this again, we have the 0.5, 1 plus 10s and root over of 2 by pi into x plus 0.044715 x cube. That's it. Now you can simply go into calling this out. Okay, we have the GELU layer. Let's say GELU layer. Then you can making it as a, let's say, GELU. And then what we have the x equal to torch dot linspace, and then you can passing here -5, let's say 200. Then you have the y is equal to GELU layer. Okay, let's say GELU layer, and then we can passing here the x, and we got here the y, and now you can simply go into printing this out. Okay, and printing this out, you can see here the value lies between the minus as well. You can use it here in the case of machine translations. So you can simply go into using here the GELU, and we need to having the GELU activation function. So this is the graph, how it look like, the GELU activation function, that you can see that just one exponential thing on here. Okay, so this is all about the activation function. Now we're going to see a different kind of problem in the activation functions called the vanishing gradient problem and exploding gradient problem. As well as you're going to see that how to choose the right activation function for the problem statement. So problems in activation function, we have the two types of problem. One is called the vanishing gradient, and another one is called the exploding gradient. So vanishing gradient, like the sigmoid activation function, certain activation function squeeze an ample input space into a small output space between 0 to 1. Because this is happening, the vanishing gradient problem is happening in the sigmoid and the 10h activation function. just because of 0 and 1 range. Therefore, a large change in the input of the sigmoid activation function will cause small changes in the output. Because while you draw the derivative of the sigmoid activation function, you can see that the range is between -3 to 3. And also the derivative curve is locally flattened. So that's why this vanishing gradient problem is happening, right? So hence the derivative became small. You can see derivative became small for shallow network with only a few layer that use this activation. Okay, because we know that sigmoid and the Tanh is nothing but used in just for shallow network. I mean, sigmoid is basically used in the last layer, and Tanh is also used as kind of the ReLU. So this is not a big problem. However, more layers are used. And we have the more layer, just like 40 up. It cannot, it causes the gradient to be small to training for the work properly. So that's why the vanishing gradient problem is still happening in the case of sigmoid activation function as well as the Tanh, because the range is between 0 to 1. हो सकते problem. Then we have exploding gradient problem. So exploding gradient problem are where significant error gradient accumulate and the result in very large update to the neural network model. That's been higher into actually changing the weight and the bias while training purpose. So if the gradient is accumulate at a large scale or the large update, the exploding gradient problem is actually happening. And an unstable network can result when there an exploding gradient problem. And the learning cannot be completed. Yes, the learning cannot be completed. That's why this problem is actually happening. The value of the weight can also become so large as to overflow. Yes, it can be possible. It can be possible to something called the non-malus, because if the weight is more greater, so it will obviously be large and try to overflow, and result is something called nan. So this is called the exploding and this is called the vanishing gradient problem. Now let's see how to choose the right activation function. To match your activation function for your output layer based on the type of prediction problem that you are solving. Let's say I'm going to solving here a binary classification, so I can using here the sigmoid activation function. If I'm going to working in a multi-class classification, I can using here the sigma softmax activation function like that. So here you should keep in mind, as a rule of thumb, you can begin with using a ReLU activation function, and moreover the activation function if the ReLU doesn't provide the optimum result. That's mean just when you're designing here any neural network architecture, first you're going to choosing here the ReLU. If the ReLU is not giving you the actual output or your the optimum result, you can go for the next one. Okay, or the next, because ReLU has so many variant. So ReLU activation function should only be used in the hidden layers. We know that. I also see that the experience in Google Colab as well. So Sigmoid, the logistic, and the Tanh function should not be used in the hidden layer. Okay, you cannot using the Sigmoid and the Tanh activation function in the hidden layer. So make the model more subspective to problem during training due to the vanishing gradient problem. Because in the sigmoid and the logistic and the Tanh, it having a problem called the vanishing gradient problem. So that's why you cannot using here in the case of hidden layer, because in the hidden layer weight and bias is updated. So Swish function is used in neural network having a depth greater than 40 layer. If you have the layer which is depth greater than 40 layer, so you can using here the Swish activation function. In the transfer learning technique, most of the actually transfer learning model having layer more than 40. You can also implement in the transfer learning model from scratch. And if you don't get here any good result, you can using the Swish activation function. So finally, a few rules for choosing the activation function for your output layer based on the type of prediction problem that you are solving. So for the regression, you can using here this linear activation function that you already see before. Then for the binary classification, you can using here the sigmoid or the logistic activation function. And for the multi-class, you can using here the softmax, because softmax is nothing but the combination of the sigmoid itself. Then you have the multi-level, you can using here the sigmoid if you have the multi-level classification in the case of YOLO. So the activation function used in the hidden layer typically chosen based on the type of neural network architecture called for the convolution neural network or the ReLU activation function. If it's not giving here your optimal value, you can go for the further one at the further ReLU activation function like ELU, SELU, GELU like that. And recurrent neural network, for this one you can using the Tanh or sigmoid activation function. Okay. Because in the case of recurrent neural network, the architecture is not like the convolution neural network, so you can using here the Tanh or the sigmoid. Okay, so that's all about the activation function and how can you implement this one and how can you choose the right activation function. So hope so you support me in the series, the AI concepts and coding from scratch, and I'll be back with another tutorial. So till then, take care and bye bye.